Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Hello, hi there, hello. Lesson 20, how far away is the moon? Good question. Opening exercise. What is a solar eclipse? And what is a lunar eclipse? Well, a solar eclipse occurs when the moon passes between the earth. So the umbria here is the moon, and the penumbra is the shadows from them. So umbria is where it's total darkness, and penumbra is where it's partial light because of one side of the sun. Anyhow, this is the moon. This is the sun, and this is the sun. This is the moon, and this is the earth. So when the moon passes between the sun and the earth, that is a solar eclipse. A lunar eclipse occurs when the earth passes between the moon and the sun. So take the moon and have it go its orbit around earth to this side. And I believe they show a picture of it on the next page. And this is where the moon would be for a lunar eclipse. So a solar eclipse occurs when the moon passes between the earth and the sun. And a lunar eclipse occurs when the earth passes between the moon and the sun. So here is a diagram of a solar eclipse. Here's the sun. So picture the sun's rays coming down, and they're going to also be here and here. Let's make them straight. And I suppose we should use a ray since it is a ray of sunshine. So these sun's rays are going to hit the earth over here, as you can see. So there's not total darkness here. And if the sun's rays are shining here and miss the moon, they're hitting the earth in some location. But as you can see, this area here, these rays start getting blocked. So it is darker in the penumbra area, but not total darkness. So here's a 3D view. So these rays of light are casting sunshine on this part of the world, but only a little bit of it is. Part of the sun is being blocked. But then there is the area, small area in the center there, where it would be total pitch, midnight darkness at that location because the sun is entirely blocked by the moon. Okay, so why are we doing this lesson? Well, if you remember back several lessons, I showed a video about Aristophanes. Is that his name? Aristophanes. Yeah, Aristophanes. Eratosthenes. Oh, anyway, he was a Greek philosopher. Eratosthenes. And he determined the circumference of the earth and how far it was from the core of the earth, the center, to the surface, so the radius of the earth, using those columns and shadows. So now we're going to use the moon and an eclipse to try to calculate how far the earth is from the moon. So let me just read you a little bit here. It says, in lesson 20, which is this lesson, students learn how to approximate the distance of the moon from the earth. Around the same time that Eratosthenes approximated the circumference of the earth, Greek astronomer Aristarchus found a way to determine the distance to the moon. Less of the history is provided in this lesson, as a more comprehensive look at eclipses has to be included alongside the central calculations. So we're going to try to provide an understandable method of how this distance was calculated, and that's what this lesson is about. Okay, so here's what we're going to talk about. A total solar eclipse lasts only a few minutes because the sun and moon appear to be the same size. So everything is moving. The earth is moving around the sun. and the moon is moving around the earth and the sun. So the moon, if you can picture spiraling around the earth, as the earth goes around the sun, the moon is going around the earth, which is going around the sun. Okay. How would appearances change if the moon were closer to the earth? So if the moon moved closer to the earth, less of the rays would be blocked. So the eclipse would be less noticeable or noticeable in a smaller area, let's say that. And the earth would, and the moon would look bigger, obviously. When something's closer, objects in mirror are closer than they appear. Okay, the closer something is, the larger it looks. The moon would appear larger and the eclipse would last longer if the moon was closer to the earth. If the moon were farther from the earth, would we experience a total solar eclipse? So if the moon was, say, way out over here, so if I drew a circle, and let's make it orange. If I drew a circle, and let's just say the moon was here instead, obviously more of the rays would be hitting the earth and a smaller portion would be totally blocking. Okay. So the moon would appear smaller because it's further away, and it would not be possible for a total solar eclipse to occur because the moon would appear as a dark dot blocking only part of the sun. Okay, so it says sketch a diagram of a solar eclipse. Well, we have it right here, so I'm not going to do that. Okay, so let's talk some more about how they calculated the distance from the moon to the earth using eclipses, eclipsi. Okay, so let's talk about this a little more. The umbria is the portion of the shadow where all sunlight is blocked. So that's the really dark triangle in there. For the purpose of our discussion today, we'll be simplifying the situation and considering only the umbria. What is remarkable about the full shadow caused by the eclipse? That is, what is remarkable about the umbria and the portion of the moon that is dark? I'll see you on the dark side of the moon, okay? Consider the relationship between 3D and 2D images of it. So here's the 3D. Let me move this up here. Okay, so here's 2D and here's what's happening 3D. So you can picture better what's happening. So if a cone represents the portion of the moon that is dark as well as the umbria, then the part that is entirely dark is a 2D image, which is an isosceles triangle. Okay, so obviously the distance from one side of the moon to the location on Earth is the same as the other side of the moon to the location on Earth. So we assume that the shadows from the moon and the Earth are all similar isosceles triangles. Okay. All right, page 2, there's going to be a lot of discussion before we continue on. So I brought in some documentation here. So there's a picture of the moon and there's a picture of the Earth. Okay, so we have, it looks like a cone, or in this case, an isosceles triangle. So the distance from the sun to this pole of the Earth is equivalent to the distance of the sun from the distance of the sun, or the distance from the sun to this pole. They're congruent. So if we were to call them isosceles triangles, then we would say that this side is congruent to this side. This is congruent to this. Be it the moon or the Earth, we're setting up a situation where we have an isosceles triangle. So you can imagine simulating a solar eclipse using a marble that is 1 inch in diameter. If you hold it 1 arm length away, like that, it will easily block more than block the sun from one eye. Do not try this at home. You will damage your eye. To make the marble just barely block the sun, it must be about 9 feet, about 108 inches away from your eye. I don't think my arm's 9 feet long, so you wouldn't be able to do it with your arm. So the cone of shadow behind the marble tapers to a point, which is where your eye is. And at this point, the marble just blocks out the sun. This means that the ratio of the length of the shadow of the marble to the diameter of the marble is about 108 inches to 1 inch. Okay, it's a 1 inch marble and it's 108 inches away. So it's a 108 to 1. Okay, so I'm just going to delete stuff as I go here. And continue on. And it says, in fact, by experimenting with different size spheres, we find that the ratio holds true regardless of the size of the sphere or circular object, as long as the sphere is at the point where it just blocks the sun from our vantage point. In other words, whether you're using a marble, a tennis ball, or a basketball to model the eclipse, the distance the sphere must be held from the eye is 108 times the diameter of the sphere. That's pretty cool. So we conclude that the ratio also holds for the moon and the earth during a solar eclipse. Since the moon and sun appear to be the same size in the sky, the moon just blocks the sun in a solar eclipse. We can conclude that the distance from the earth to the moon must also be roughly 108 times the diameter of the moon. It's a neat way to think about that, because the earth is at the tip of the moon's shadow. This is kind of cool. So now it says, let us consider what's happening in a lunar eclipse. A lunar eclipse occurs when the moon passes behind the earth, as in this diagram. Once again, the earth, sun, and moon lie on a straight line, but this time the earth is between the moon and the sun. Consequently, during a lunar eclipse, the moon is still faintly visible from the earth because of light reflected off of the earth. Okay, and then finally we'll say, based on what we know about the ratio of distances for an object to just block the sun, we can conclude that the moon must be within 108 Earth diameters. If it were not within that distance, it would not pass through the Earth's shadow, and the Earth could not block the sun out completely. Studying total lunar eclipses was critical to finding the distance to the moon. Other types of eclipses exist, but they involve the penumbra. The following measurement required a total eclipse, or one involving the umbra. By carefully examining the shadow of the Earth during a total lunar eclipse, it was determined that the width, or more specifically the diameter, of the cross-section of the Earth's conical shadow at the distance of the moon is about 2½ moons. So they're saying right here is 2½ the diameter of the moon. Is that right? The cross section of the Earth's conical shadow is 2½ times the moon's diameter. Okay, so there's some information on lunar and solar eclipses. So here is example A. If the circumference of the Earth is about 25,000 miles, what is the Earth's diameter in miles? Okay, so for starters, circumference equals 2 pi r, or circumference equals pi d, because 2r is d. 2 radii is equal to 1 diameter. So when we're talking about diameter in miles, we're not going to use the radius equation. We're going to use the circumference equation. So the first thing I would do is say C equals pi d. If the circumference of the Earth is about 25,000 miles, what is the Earth's diameter? So I want to solve this for d. And in order to do that, we divide both sides by pi. And these pi's cancel, and we get d equals circumference divided by pi. And we know the circumference is 25,000 miles. And we're going to divide that by pi. So if I take my calculator and do 25,000 divided by pi, I get 7957.75. miles. So the Earth's diameter is approximately, so we're talking draw a straight line from the North Pole to the South Pole through the center of the Earth, and it would be 7,957.75 miles. Okay, so let's approximate that to make this easier. So let's just say it's approximately 8,000 miles. All right, so the diameter of the Earth, approximately 8,000 miles. All right, page 2, this does not look like anything in your book because I'm just brought in everything we need to discuss before we focus on what they're asking on page 2. So it says, based on what you know about the shadows of the moon and the Earth, what do we know about the measures of angle ABF and angle BEC in this diagram below? So if I look at angle ABF, it's right here, and angle BEC is way down here. Okay, well, if we took this moon and moved it up like so, this line is parallel to DC. The lines are parallel. So AB is parallel to DC. This is a parallelogram. So if they're parallel, then EB is a transversal through two parallel lines, and therefore we have alternate interior angles, and alternate interior angles are congruent. So we know they are congruent. The angle measures are equal since we are assuming the shadows can be modeled by similar isosceles triangles. Okay, since they're isosceles triangles, that's the, we set one on top of the other. Let me get rid of these marks. Okay. What is the relationship between AF and AB? So AF is the diameter of the moon. AB is a side. Since the distance an object must be from the eye blocking the sun is 108 times the object's diameter, the length of AB must be 108 AF. So if AF is 1 unit, AB is 108 units. Obviously, this is not to scale. Okay. What is the relationship between AF and FD? Okay, one's the diameter of the moon, and this is 2.5 units. We know that the diameter of the cross-section of the Earth's conical shadow at a distance of the moon is about 2.5 the moon's diameter. So we said that earlier. So if this is 1, this is 2.5 times. So AF or FD is 2.5 times the length of AF. So if AF is 1, FD is 2.5. Okay. So reversing the moon's shadow completes parallelogram ABCD. This is now a parallelogram. We can now be sure that ABCD is a parallelogram. Allow students time to discuss why this must be true. Why is that true? Okay. This is a trapezoid, and this is an isosceles triangle. This side is shared, so we know BF is congruent to AB, and we could move AB down to DC, and it would be congruent to that. So we have two legs of a quadrilateral, and FD is parallel to BC, and that forms a trapezoid. AD must be parallel. AD must be parallel to BC. Okay, so this is parallel to this by construction. The diameter of the Earth is parallel to the segment formed by the moon's diameter and the diameter of the shadow at the distance of the moon. We know that the measure of angle ABF right here equals the measure of angle BEC down here, since the shadows are similar triangles. This means that AB is parallel to DC. So we have two isosceles triangles, so they're similar, and therefore the angles are congruent. So then we get the alternate interior angles from that. Okay. Okay, so continuing on now, since we know ABCD is a parallelogram, then AD, so that's AF plus FD, equals BC, which is the diameter of the Earth. So 2.5 plus 1 is 3.5. So now we're saying the Earth is 3.5 units, which is approximately 8,000 miles, according to our answer from page 1. So from our work in lesson 19, we know the Greeks had the circumference of the Earth at this time, which means they also had the Earth's diameter. Then it was known that BC was about 8,000 miles. So we know BC is approximately 8,000 miles from B to C. Okay, so then we have this equal to that. So 3.5 units is 8,000 miles. So you take, what they did here was they took 8,000 divided by 3.5, and it comes out to be 2,285, and they rounded to 2,300, therefore the approximation. We already know that the distance from the moon to the Earth is 108 times the diameter of the moon. Okay. If the moon has a diameter of 2,300 miles, then the distance from the moon to the Earth is roughly 2,300 times 108 miles, or 248,000 miles. With some careful observation and measurement of that lunar eclipse and basic geometry, Aristarchus was able to determine a fairly accurate measure of distance from the Earth to the moon. Okay, so we don't like using decimals. Let me erase this. We don't like to use decimals in proportional setups. We don't like to say 3.5 is to 1. So we would double that to get 7 is to 2. Okay, so that's where I'm going to get this next value. So we're comparing it. It's 2 sevens, 2 to 7. Okay, so what we're going to do for part B is we're going to say 2 is to 7 as 25,000 and let me just see something. Okay, if I get back to here, we're using the information here, 25,000. Okay, lost track of that for a minute. So we're saying the circumference of the Earth is 25,000 miles. So using that information of 2 is to 7 as 25,000 is to pi. Is how we're going to find the moon's diameter. So what we did was we took 25,000 divided by pi to get that 8,000. And then we're going to take 2/7 of that is basically what's going on here. So when we do that, we're going to get approximately. So if I cross multiplied, I would do 25,000 times 7 and then divide that by 2 pi. And I need to do parentheses if I'm going to do that. Okay. No, that's not what we're doing. We're going to take 2/7 times, I'm setting up a proportion here, my fault. All right, it's 2/7 of 25,000 over pi. Well, we already did the 25,000 divided by pi right here. And we got approximately 8,000 miles. So really what we're doing is taking 2/7 of 8,000, which equals 16,000 divided by 7. And that comes out to be about, do approximations, 2,300 miles. Okay, so the moon's diameter is approximately 2,300 miles. So from A to F in the real world, we're looking at 2,300 miles. Then it says how far away is the moon in miles. So then what we're going to do is just simply take the 108 times, remember that 108 times the distance of something, and we're going to multiply that by our 2/7, and then we're going to multiply that by that 25,000 divided by pi, which was 8,000. So really what we're doing is we're taking this 2,300 now and multiplying it by 108. So if I just go here and say times 108 equals 246,857. So that's approximately 247,000 miles from Earth. Okay, so just doing those calculations is actually pretty cool how we came up with the distance to the moon. And that was done way back in Aristocracy, and what were their names? Can't even remember now. Aristocrates, not Aristotle, Aristocrates and the other guy. All righty. So they did that without any major calculations other than what happened on days of eclipses. Okay, page 3 brings us to the end of lesson 20. Go to your problem set.